Every robotics builder reaches the same moment. It doesn't work. In this lesson, we'll turn that frustration into a method. You'll learn how to test wiring, code, sensors, power, and Wi-Fi. Then improve your ESP32 project with confidence. So far, you've learned how robots think, how ESP32 circuits connect, and how sensors, motors, Bluetooth, Wi-Fi, and IoT projects work together. Now we shift from building to engineering, testing carefully, finding faults, and improving reliability before moving into more advanced robotics hardware. When a robot fails, beginners often panic or guess. Engineers debug. They ask what changed, test one cause at a time, and observe carefully. That habit turns problems into clues and helps protect your robot while you improve it. Good debugging starts before you touch the circuit or edit the code. First, predict what should happen. Then observe what is actually happening. Compare the two and look for the gap. Break the project into smaller parts: input, processing, output, and power. Test one part at a time so you know where the problem lives. Keep a simple debugging notebook with what you tried and what changed. Even a small clue matters because each clue removes a guess and moves you closer to a real fix. If an ESP32 project does not behave as expected, begin with the simplest possibility: the wiring. Press each jumper wire firmly into the breadboard and the ESP32 header. Verify the exact pin number, not just the approximate location, because GPIO labels can be easy to misread. Check the breadboard row as well, since holes that look separate may be electrically connected. Finally, compare your build to the circuit diagram one wire at a time. Slow inspection here can save much longer debugging later. Electricity needs a complete path, like a loop road. Current leaves the power source and must have a safe way back through ground. Parts like LEDs, buzzers, batteries, and some sensors also care which direction they face. Reverse the positive and negative connections, and the part may stay off, heat up, or fail. Make sure connected modules share the same GND reference, so signals mean the same thing. And never feed power straight into a signal pin unless the circuit specifically calls for it. Power problems can look exactly like code problems, so test power before rewriting anything. A battery may light an LED and still fail when motors start or Wi-Fi transmits, because those moments demand much more current. Watch for resets, slow motors, flickering sensors, or dropped connections. Check that the ESP32 and every component receive the correct voltage under load, not just while idle. If behavior changes when you recharge, replace, or use a stronger supply, you have found the real cause. When your program fails before it runs, start with syntax. A missing semicolon, bracket, or quote can confuse the compiler and create an error that looks bigger than it is. Compile, read the first error message, and check the nearby line carefully. Fix one problem, then compile again. If the code compiles but will not upload, switch from code to connection. Confirm the ESP32 board selection, the correct port, and the USB cable. Debugging is a loop. Read, fix, test, repeat. If the program uploads but the robot acts wrong, the ESP32 is probably doing exactly what your code told it to do, not what you meant. Check the decision points first. A single symbol can flip the behavior, such as using greater than when the robot should react to something closer. Then check loops. They may repeat so fast that an action is skipped or keep running forever. Finally, verify that variables update where you expect. Add serial.println to print values as the program runs and follow the logic step by step. Delay is simple, but it is also blocking. When code runs delay 2000, the robot is basically waiting for 2 seconds. During that wait, it may not check buttons, read an obstacle sensor, or respond to a Wi-Fi command. That is why programs with many long delays can feel sluggish. Short delays are still useful for smoothing motion or making code readable. But for responsive robots, use millis-based timing. Check the clock, keep looping, and keep listening while deciding when the next action should happen. Sensors rarely give perfect numbers. Before writing if statements, print the raw values and watch how they change in the actual room. A light sensor may read very differently near a window than under a desk. An ultrasonic sensor may jump when surfaces are angled. Soil readings shift with pot size and moisture level. Use those real values to choose thresholds, then test both sides of the decision. Calibration means tuning the code and setup until the project behaves reliably where it will actually be used. Wireless problems are easiest to solve when you test the chain one link at a time. Start with the ESP32 credentials. The network name and password must match exactly, including capital letters and hidden spaces. Then use the serial monitor. A successful connection should show Wi-Fi connected and an IP address. If you are opening a local web page, make sure your phone or laptop is on the same Wi-Fi network. For alerts, separate the tests. First, confirm the sensor changes correctly, then confirm the dashboard, email, or message service receives the event. For a full ESP32 project, resist the urge to debug everything at once. Start with power, because unstable voltage can make good code look broken. Then test each hardware part by itself. One LED, one sensor, one motor, one relay. After that, test the code in small pieces. Read the sensor, check the decision logic, and then trigger the output. When you make a fix, run the full system again and write down what changed. This loop turns debugging from guessing into a repeatable engineering habit. Debugging gets your robot working. Engineering improvements help keep it working. Label important connections so repairs are faster. Secure boards, batteries, sensors, and cables so movement does not shake anything loose. Add clear feedback, such as LEDs, buzzers, serial messages, or status displays. These small upgrades turn a fragile prototype into a project that feels reliable, understandable, and professional. Troubleshooting ESP32 robots comes down to checking the right suspects: hardware, code, power, sensors, and wireless links. Strong engineers test one part at a time, use evidence, and improve the design after each fix. That makes robots safer, cleaner, and more reliable. Next, we'll carry these habits into Arduino Robotics and build dependable hardware control projects.